Next up, we have Varun Mukund. He is an integration platform administrator at Charles Darwin University. He's going to be sharing with you CDU's Evented API framework. Varun, take it away.
Good day, Muleys. Thank you for tuning into this session today. Wherever in the world you are watching this from, I hope you are keeping safe and keeping healthy. So let's get us started. Today I'll be speaking about how we at Charles Darwin University utilize the capabilities of MuleSoft to provision a dynamic and configurable framework for data provisioning within CDU. We'll go into the details of the architecture and the technical solution which we came up with, and how we utilize various concepts like API-led and event-driven architecture to achieve our goals. We'll begin the session by talking about the vision which we have at CDU for integration using API-led and event-driven architecture. We'll then have a look at how we arrived at selecting the components required to build a solution for us. I will then walk you through the high-level details of the pilot project which we had chosen to implement the solution. And finally, we'll be moving on to the fun bits. I'll be talking about the integration architecture and the technical details of the solution which we had built. So let's get started. I would like to now talk about the vision which we have at CDU, which has inspired to come up with this framework. CDU, similar to a lot of other organizations, currently is undergoing a major digital transformation program. Now, our desire is to provide the best in class digital experience to our students and to our staff. The approach from CDU in this particular direction has been primarily to invest in different best of breed solutions. And these best of breed solutions, they cater to different business functions within the university. We have functions like student administration, learning management, library, placements, curriculum, and so on. Now, what we would find today with most contemporary modern systems is that they usually come with their own rich set of either SOAP or REST APIs, and they expect the data either to be pushed to them or pulled by them using their own APIs. You don't expect them building any custom experience API layers, if you were to call it that. Similarly, many of these new age systems, they are also event enabled. Now, what I mean by event enabled is that these systems, they usually have the capability to capture the different business transactions which are happening within their system and make them available as an event which could be subscribed to. And these transactions which are published by these systems, these can be consumed by any interested party. An interested party could either be a downstream system, or it could even be a third party, like the government. And this is just to give a few examples. Now, with this in mind, and to future-proof CDU's process for data provisioning between systems, we jotted down 3 key vision requirements. We wanted to enable the different lines of businesses within the university to explore, discover, and subscribe to events linked with a data object across the different applications at a central location. We wanted to provide some flexibility to select and choose only the requested and respective fields or attributes of the data objects which are required by the lines of businesses. This is rather important for us because apart from reducing the overall load of data transfer by reducing the number of fields, this step also ensures that the attributes provided are exactly what the customer requires, nothing more, nothing less. And leading on from the second requirement, we wanted to implement a manual governance flow before provisioning any kind of data to the line of business. We want to ensure that there is approval from the data owner for the fields which are requested by a particular line of business. From the vision statement, we know what are the three key things which we are looking at. We are looking at discoverability, flexibility, and governance. It was now time to start thinking about designing a framework to achieve this vision. At a high level, we first started by identifying the various components that we would need to achieve this particular outcome. Now, since MuleSoft and its Anypoint platform was a key enabler for our digital transformation program already, we didn't have to look too far for our components. Straight away, we decided that we would like to leverage Anypoint Exchange for discoverability of the event objects. Another no-brainer was to select DataWeave for any kind of transformation or filtering requirements. Now, one key thing as part of this design, it was very clear to us that we would need some sort of a central processing engine which would be able to determine the details of the interested consumers for our data, and it should also be able to store and retrieve any transformation scripts which are needed to be executed for that consumer. To solve this intermediate persistence requirement, we decided to use database tables. We at CDU were already having multiple database servers running on Oracle database. We were running a plethora of applications on CDU on these Oracle database servers. It became a natural choice for us to create a schema in an existing database server for our usage. Now, the moment we started to create these tables, it was mandatory any kind of performance is also taken care of. Now, to complement these tables for a faster performance, we decided to cache our data in our Mule apps using Object Store. Now, lastly, with any event-driven architecture design, one core component needed is a messaging infrastructure or an event bus. We utilize RabbitMQ as our messaging platform to complement Mule's enterprise service bus. This ensured that reliability and guaranteed delivery aspects of integration design is fully covered. And we are also in a position to implement a robust error handling and retry mechanism. Now, with all the components decided, we now had to choose an integration pattern which would rather be sitting at the heart of this solution. The best fit pattern, which we thought would complement the event-driven architecture along with the API-led approach, would be the webhooks concept. Now, many established cloud applications, be it Facebook or Google, Instagram, or even GitHub, come with their own webhooks. The concept is very simple. If anyone is interested in feeds or events happening in these applications, all you need to do in most cases is to provide an HTTP URL, which is also known as a callback URL. And these applications, whenever there is an event generated, can post the data to these callback URL. To give you an example, say you have posted something on Facebook. The moment you receive a like, that's an event which is generated within Facebook, and that like event can be sent as a payload to any HTTP callback URL which you have defined, and that payload would be sent over to your URL as a post request. Now, with the components and the pattern in mind, we had to choose a pilot project. Now, luckily, CDU was undergoing a project to implement Oracle HCM on the cloud. Now, as this system was the source of truth for all staff and employee information for CDU, the implementation of this system would naturally have a downstream impact on multiple other systems within our organization. And with this, there was an immediate need which was originating to build integrations to all these different downstream systems. Now, we saw this as an opportunity, and we decided to start work on the framework by choosing the integration with Oracle HCM as the pilot. We started to put the pieces together now. First thing we had to find out was whether Oracle HCM was capable of generating any events. What our research led us was discovering the Atom Feeds functionality, which is built in within Oracle Cloud for capturing workforce structures and employment changes happening within Oracle HCM. Parallelly, we also had to design a database table structure for storing the list of subscribers for HCM data, their filter condition, and any subscriber specific transformation script. Now, we also needed to ensure that while designing these tables, the table structure should be common, reusable, and most importantly, any interactions happening with the table are API enabled. Okay, so let's get into the fun bits now, starting with the integration architecture. The highlighted portion in this diagram represents the system API layer of our solution. The systems in action here are Oracle HCM naturally, and the Oracle database tables, which has the callback registration tables. Now, finally, we have our two subscriber systems or the downstream systems, and these are IDM, which stands for Identity Management, and SRS, which stands for our Supplementary Research System. We are abstracting the connections to these subscriber systems using their own individual system APIs. We are doing this for better security and granularity. Let's get into the details of the system API which we built at Oracle HCM end. The system API for Oracle HCM provides three key functionalities. It provides an option for a consumer to subscribe to events. There is an engine built in the system API which is capable of generating events. And lastly, there's a resource endpoint which is capable of generating the event context or the complete payload, which is relevant for a type of event generated. Now, let's come to the subscription part. We achieve subscription by providing a REST endpoint with the naming convention of /data object /subscribe. The data object is the data object of the event which is being generated. So if an event is corresponding to change or hire of an employee, the data object is employee. The body of the post request for this particular endpoint contains details like the interested subscriber, its system name, email, the callback URL, and the data attributes. The key bit here is the data attributes. They define what are the fields which are needed by the downstream system. How we do that is we mock the JSON of the complete event context or the object. So what you see here is the complete employee object, and we make each field as a Boolean. Now, if a subscriber is interested in a particular field of the JSON, all they need to do is to provide true against that field which they are interested in. Now, all this input is taken and stored in the callback registration tables. Even a dynamic data weave script is generated and stored in the callback table based on the attributes sent and the value sent in those attributes, whether they are true or false. Now, the next bit is the generation of events. For this, we have a scheduler which polls the HCM Atom feeds regularly, generates a common event JSON, and publishes the event to RabbitMQ. Now, finally, as you can see, the event JSON is quite limited in its structure. It just notifies that there has been a change and gives you the resource href to get further details. We have exposed the href in the resource as part of the system API. So what you see in the diagram here, /worker/ID, that href is available as a resource in the system API, and you can call that resource and get the complete event context or the complete payload which is linked to that event. We'll see later on when I explain the design of the process API layer on how this href is used. What you see here is the entity relationship diagram of our callback registration tables. As part of releasing any API with subscription capabilities, we make an entry for the API and its resources in the Mule underscore app, the Mule underscore app underscore API, and the API underscore resource tables. Whenever a subscription request is received, entries are made in the callback table, the client table, the client underscore data weave table, and the data weave table. The access to these APIs are also via API. Access to these tables, are also via APIs. The structure of these tables is flexible enough to accommodate any API and any resource, and if required, it can also execute multiple data weave scripts in a sequence, if that is required. The final set of components on the system API layer are the system APIs on the two subscriber applications. Now, we did not want to post data directly to the callback URLs. Rather, we would like to have a layer of abstraction using system APIs for those applications. The execution is rather simple and consists of two steps. We implement a listener, which is expecting an HTTP post request on a /publish endpoint, and all it does is to take the message and push it to RabbitMQ. And from there on, we have a second step which basically listens to messages in RabbitMQ and calls the callback URL for that particular system. Now you'd ask me why we have this two-step process. This literally technically can be achieved in a single step wherein I have a listener and I simply call the callback endpoint. But by segregating it into two steps, it decouples the error handling for us from the process API layer. And also, it enables us to extend this framework for systems which are not capable of providing a callback URL. Now, for example, let's take a system which is capable of accepting only files on an SFTP server. We can now integrate to that system without touching the core process layer. Now, finally, coming to the main processing engine. Here, we have created a process API Mule application. The very first thing which the Mule app does as soon as it starts up is to store the registration details from the callback tables into an object store. And this process is also running on a scheduler once a day to update if there's any new registration data which is available in the callback tables onto back to the object store cache. This ensures that we have a local cache available within our Mule app and we don't hit the callback tables repeatedly. As soon as an event is generated by the source system, we have a listener configured in our process API which is listening to those events. This Mule app listens to the RabbitMQ queue for any events which are generated, and then it checks if the event type is associated with a callback entry by making an entry check in the object store cache. If an entry is found in the callback cache for the generated event type, the flow then uses the href data which is part of the event payload which I had shown you earlier. It uses the href data in the event and retrieves the event context payload by calling the HCM system API back. It then determines the list of consumers which are registered for that event and duplicates the event context payload for each consumer and publishes the context payload along with the context information back to RabbitMQ. Now, this is again an optional step. You could actually call the system API for the subscriber here directly. But again, I'm using a two-step process. I'm generating the event context payload from the event, and then duplicating that payload for each individual consumer. Again, this two-step process has been put in place purely from an error handling mechanism point of view to segregate the error handling for each different consumer separately. The next step in the process is to consume the event context payload for a specific consumer from RabbitMQ. The payload is taken and then transformed by executing the data weave script specific to each consumer. Now, if you remember, we have the script which is needed to be executed already available on the object store. The object store was initially loaded when the Mule app first started and then is regularly updated every day. Now, we have added another optional step for you. This is a step which can determine whether a particular event context needs to be filtered out for a consumer or not. Now, let me give you the scenario which we had. We have SRS, which is our supplementary research system, configured as a downstream system and listening for employee data. It is only interested in those employees, those staff who are also a researcher within CDU. We were able to dynamically determine the filter using the same condition and using the same framework. All we had to do was to execute a data weave script which returned either a true or a false and then go on continue in the flow. Now finally, once all the transformation is completed, what we had to do was to call the slash publish endpoint which we had spoken about in the previous slides and send the transformed JSON back to the publish endpoint of the respective system APIs. The core critical MuleSoft component which allows us to use and design this framework is the dynamic evaluate component. Basically, that component allows us to take a data wave script which is literally stored in database tables and then object store to read it as a text, store it in a variable, and then execute that script using the dynamic evaluate component. Now that concludes the design aspect of the solution. Before I finish, I would like to recap the key takeaways and the benefits that we have realized at CDU by implementing this framework. Starting with discoverability of assets and the event objects using Exchange. There is high reuse with this framework, and this framework basically enables a new consumer to get added into the process API without making any changes to the process API code base. We gain flexibility by giving the option back to the consumer or the line of business by giving them the flexibility in selecting the fields that they need. And finally, we were able to implement a governance workflow approval process before publishing the data to interested parties. How we achieve that? If you remember the slash subscribe endpoint as part of our system APIs, whenever anybody makes a subscription, that goes and sits into the callback registration tables with the status of pending. And only if the status is changed from pending to approved is the data available and is read by the process API engine for the downstream systems. That concludes my presentation. I hope it was useful and helpful to you in some regards. Thank you.